So far, we've done hypothesis testing with either one mean or with two means. In this section, we will be comparing three or more means. To do this, we use the F distribution along with a technique called analysis of variance. Now, these problems will only have one independent variable, so the process is called one-way analysis of variance. So one-way analysis of variance, or Anova, is a hypothesis test used to compare three or more population means. The null hypothesis for the Anova test always states that all population means are equal. The alternative hypothesis always states at least one mean is different from the others. And if you're doing an Anova test by hand, there's a lot of steps. And I'll go into these steps in more detail on question 1. A medical team wants to determine whether there is a difference in the mean lengths of time it takes 3 types of medication to provide relief from headache pain. Several people with headaches are randomly selected and given one of 3 medications. Each person records the time in minutes it takes before the medication begins to work. The results are shown in the table below. At alpha equal to 0.05, can you conclude that at least one mean time is different from the others? Assume that each population of relief times is normally distributed and that the population variances are equal. Use the rejection region method and show will work. So the claim is that at least one mean is different from the others. And this is the alternative hypothesis. So the null hypothesis says that mu1 is equal to mu2 is equal to mu3. So they're all equal. Alpha is 0.05. Now again, when solving Anova tests by hand, there's a lot of steps. So first we have to identify the sample sizes. Sample 1 size is 4, sample 2 size is 5, sample 3 size is 4. Next we have to calculate the sample means. Sample 1 mean is 14, sample 2 mean is 17, and sample 3 mean is 16.5. The 3 sample variances have already been calculated for us. Next is the number of samples, which is k. So that is 3. And the sum of the sample sizes, or capital N, is 4 plus 5 plus 4, which is 13. The grand mean, or x double bar, is the mean of all of the data entries across all of the samples. So if we add up all of the data entries and divide by capital N, which is 13, we get 15.92. Next, we have 2 types of degrees of freedom. For the degrees of freedom in the numerator, we take k minus 1, which will be 2. For the degrees of freedom in the denominator, we take capital N minus k, which will be 10. SSB stands for the sum of squares between the samples, and we need to take each sample mean minus the grand mean, square that, and multiply it by the sample size, and then add those together. And we get 21.9232. SSW stands for the sum of squares within the samples, and we need to take each sample size minus 1 and multiply it by the sample variance, and then add those together. And we get 73. MSB stands for the mean square between, and we need to take SSB and divide it by the degrees of freedom for the numerator. So 21.9232 divided by 2 is equal to 10.9616. MSW stands for the mean square within, and we need to take SSW and divide it by the degrees of freedom for the denominator. So 73 divided by 10, which is 7.3. Finally, for our test statistic, we have to take MSB and divide it by MSW. So 10.9616 divided by 7.3, which is 1.50. And the critical value, if we refer to the table, is 4.10. So the picture looks like this, and F goes right here. So F is not in the rejection region, which means we failed to reject the null hypothesis. And the conclusion would be, at the 0.05 level of significance, there is not enough evidence to conclude that at least one mean is different. So this was definitely a very long calculation. It will be way faster using the calculator.